예, 이번 시간은 리눅스 커널 인스트루멘테이션 인 파이썬에 대해서 팽리 님이 발표를 해주시겠습니다. 예, 큰 박수 부탁드리겠습니다.
Good afternoon, everybody. I'm Feng Li from China. I'm very happy to meet you here. And today I will share you with talk about Linux Kernel instrument in Python. Firstly, let's quickly go through the content of this speech, which can be divided into 4 parts. Part 1 is about eBPF and BCC. Part 2 will show in kernel Python associated in kernel virtual machine. And in part 3, we will demo Python assisted, discuss the Python assisted DataCenter development. And a quick summary, a brief summary will be given at the last part. Let's start by take a look at the tracing landscape of Linux. As we know that the well-known instrumentation tools like trace command or perf or system type on Linux leverage the event tracer that exposed by the debugger or trace file systems or via system calls, related system calls to gather the trace event, and which is built on top of the underlying Linux kernel instrument mechanisms like keyproofs, uproofs, and trace pointers. And let's move to what eBPF is. Actually, eBPF comes from the BPF, which is also known as Berkeley packet filter, which we often know it as CBPF. It was introduced in kernel version in nearly 1 decade before. It was originally designed for packet filtering, which means the bytecode will be compiled from the filtering rules that will be executed in kernel BPF virtual machine, which can be used by the user space utilities such like TCP dump. It can also be used for security or traffic control related application field. And eBPF means extended BPF, which was the first added to the Linux kernel since version 3.15, and keep on developing. It is aimed at being a universal in kernel virtual machine. Actually, it changes the older ways for kernel instrumentation in some extent, and it is said that it is a good alternative to the toolkit like system tape and running faster than the trace. In our world, eBPF has changed the older ways for kernel instrumentation. Here is the table for comparison between the classical BPF and the extended BPF. We can see from it that many new registers and instructions has been added into eBPF. So it serves more service, like has the ability to call in-kernel helper functions or it also has some GRT supported that better mapping with new architectures for jittering. The eBPF also gets a strong support from LLVM, and as it is still under developing, so eBPF the platforms that eBPF supported is still less than the CBPF. And additionally, there is a new system call which named BPF was added in the latest kernel version to support eBPF. Here, in generally, there are some methods to develop eBPF program. You may directly write it in BPF assembly, or you may write it using C language and compile it with LLVM. And the third method is to develop it with the BCC, which we will talk about later. The general working flow of eBPF program is described as the following graph. When the application is developed with its kernel part code that compiled to the BPF bytecode, the program will be loaded to the kernel space via the BPF system call, and it will be doing down the strict static check in a verifier to ensure security, and the checked bytecode will be executed in a BPF VM, which can be configured in interpreter model or just-in-time execution model. And the user land part of this program and the kernel part of the eBPF program can be communicated via mapper-related mechanism in the kernel with the help of the internal helper functions and the BPF system calls. And with the help of internal helper functions and some macros that define the kernel, like the PBF program run kernel macro, it can be interacted with the other subsystems in the kernel. The BPF, the BCC means the BPF compiler connection. It is a toolkit with Python and Lua front-end for compiling, loading, and executing BPF programs, which will also use a defined instrument on a new kernel image. Generally, it can compile a BPF program from a restricted C source code and attach a BPF program to keyboard, UProbe, trace point, or use USDT or socket, and pour the data from a BPF program. In a word, it is a framework for building routers or one-off scripts for kernel instrument. Here, many companies have developed various BCC tools for Linux kernel instrument, which covers many kernel subsystems such like file systems, network, scheduler, or device driver, or memory. Since BCC is born with Python, so Python is given the fullest support in BCC. Here is the architecture of how BCC program is running. As we just said that the registered BPF C code is embedded in Python or Lua program, and this restricted BPF C code will be compiled into bytecode that will be running in the kernel. And BCC use modified clan and LLVM based solution to rewrite the restricted BPF C code and compile it with the clan and LLVM front end. Here is the tracing landscape for the how eBPF can be used for the Linux kernel instrument, and the processor and its subcomponent we have just explained. Here is the example about how BCC is really worked. This example is directly from the official BCC source code, which under the following path. It is about the random reader functionality. As we know that we may run it directly from the installed BCC path, which you may directly on the folder under the following path and run this Python script as root, and it will listen to the uRead event, trace event, and in another shell you may run the utility dd to trigger some trace event, and as we can see that if you run the following dd command, the random trace random reader .python will show the following data that it was collected from kernel instrument. Let us check the source code of the random reader. There are two versions for this program. One version is a generic BCC program, which, as you can see from the code in earthy yellow color, which is embedded C source code that embedded in the Python program. The first, it defines a structure which wraps the trace event that defined in the about the trace point against random read in the kernel, and it has, the program started for tracing by reading the data from the trace pipe from in the sys systems, and actually in order to help programs to develop the BCC program against eBPF more easily, in the internal of BCC implementation, they have some macros such like trace point probe to simplify the embedded restricted C code. So you may also write the code in the following method. Then the embedded restricted code will be imported to the compiler of BCC, which is based on the Klan and LLM as we explained before. It will utilize the rewriting mechanism in the Klan to rewrite this embedded C code into the operator version that will be compiled into BPF bytecode. And for in kernel virtual machine, kplugs comes from a Python library that could compile a subset of Python language to the kplugs bytecode, which could be running in the kplugs virtual machine in the kernel. The kplugs program in user space meaning consists of two modular files, which means kplugs.py and core.py. Kplugs program use the interface defined in kplugs.py for programming, and the internal functionality was defined in the core.py, which also includes the compiler that will compile a subset of the Python language via AST package to the kplugs bytecode. Then the compiled kplugs code will be loaded to the kernel space via C types. sorry. The K-Plex pseudo device is the interface between the kernel space and the user space program. And the K-Plex virtual machine is presented as the driver of this pseudo device. The K-Plex has the following four functionalities, such like access all the system memories and or resolve kernel symbols, hook kernel functions, or just call exported kernel function. So let us check hook sample about how K-Plex works. Here is the hook sample program that in Python language it is a simple, just a simple example. It will import K-Plex package module that and create a hook handler that register it with the that it aims at trying to hook the sysclone internal system call. In another share, we may load this module to the kernel and check and clean up the message before testing. And in this share, we may run this Python script and we'll check the output of this program. So this program was triggered by another native application, which is a multi-thread application that uses the pthread library. It is a simple native application, just create a 5 thread in a program. So as we know that the fork-related system call will finally call the sysclone internal functions in the Linux kernel. So the trigger application, when the trigger application is running, the screen will printed the information that we just hooked. And as we check the source, when we check the source code of the internal implementation of the hook functionality, we found that in the source code of K-Plex, it is actually just use the kprobe underlying infrastructure in the kernel, and the code, the internal code within the hook is just register, just fill the fields of kprobe structures, and invoke the functionality like register kprobe or unregister kprobe. And in order to compare the K-Plex for the upstream kernel version, you may use my fork version of this project as the following pass URL on the GitHub. And some tips for debugging K-Plex related programs. As we know that you may use this command in the kernel space to tracing details, internal details, the execution result for user space Python program, and for developing Linux kernels modular like against the K-Plex, you may use some integrated development environment such like OneShot kernel. Here is in addition to Linux instrument, the eBPF and there are some other application files for the scripting language against the kernel. As we know that the NetBSD organization has implemented kernel scripting with Lua in their recent NetBSD releases. Here is a bigger picture of what NetBSD is trying to implement the kernel scripting with Lua. In userland, there are some utilities to help to load Lua scripting scripts or some programs or some compilers to. And in kernel, there are Lua, there are embedded Lua runtime environment in the kernel to try to execute the script loader from the user space. And there are Lua bindings for Lua program to communicate with or interact with the other kernel subsystems. Actually, the current implementation for this kernel scripting on latest NetBSD version does not support GIT. But there are two projects on Linux that successfully embedded Lua runtime environment with GIT support on the Linux platform. When the developers of Lua was asked that why do they not choose Python as the kernel scripting language, they said that because Python has a huge library and the memory contribution on Python is not affordable, and direct object mapping is also difficult to embed it in the kernel. Because the size of Python VM is at megabytes level, while that of Lua, as we know, that is a concise and fully customized implementation, which at kilobytes. So they choose Lua as the kernel scripting language. But as we can see from the project like Kplus, that Kplus, actually we do not need to implement a full language set against virtual machine implementation for Python in the kernel. And actually we even do not need to compile the Python front end into the Python script. We may define a specific bytecode set that could run in the compile the Python program better suited for the kernel executing. And in conclusion, kernel scripting could greatly reduce may do favor to reduce the size of kernel sources. As we know that in the past decade, the code size of the Linux kernel has been growing rapidly. Kernel scripting will sure to do favor for it. And the most of the thing is that kernel scripting will deliver a high-level programming environment to the kernel, and let the user explore the system in an easy way. In a word, it is a great innovation in OS development. And in part 3, as we know that in the real world, the computing system, the complex computing system consists of many heterogeneous computing units, such as in hardware perspective, such like CPU, GPU, or DSP, or FPGA, and from storage perspective, maybe various storage components. The most important thing for HPC computing, related computing today, is to how to make fully use of those heterogeneous computing hardware, and while still provide enough abstraction to the upper layer programs or developers. Alexander is a cool object from the powered by Python for open source modern analytics platforms. It is a Swiss knife for big data, artificial intelligence, HPC, and so on. And Intel has also noted the potential for Python in the HPC or cloud computing field. They are working on developing a special distribution for Python, which can be accelerated with their MKR, MPI, and TBB or DAL libraries on the x86 platforms. Their test results show performance will boost on some selected numeric functions. For AMD, their famous HSA platform has also added Python as one of the programming languages that is supported. And as we can see from many, as we know that today there are many terminologies such like software-defined data center, software-defined networking, or software-defined storage, and so on. Traditionally, software-defined, maybe the trend is software-defined everything for tomorrow's computing system. That they will means use software-defined system means they will use generic hardwares and automated development or deployment or some DevOps related things. And IOWiser is an organization that that funded by many industry-leading companies to engage to facilitate the development or construct architecture reconstruct and technology innovations for network or data center related technologies. And BCC, the BPF compiler tools that we mentioned just previously is come from their products. And actually it includes the P4 front end in the BCC source code, which we implemented in pure Python. As we know that P4 is the domain-specific language for network virtualization. Finally, I will give a brief summary. As we can see from what we have talked today, that the trend for the computing related technology is that user space and kernel space repartition and unifying, which means you can write your function in kernel space in user space while running it in the kernel space. And some testing migration result has shows that some user space drivers could gain much better performance when compared with what running in the kernel, and as we have talked about, as we have mentioned in part 2, that you may scripting OS scripting will have many benefits. And today, compilation related technologies are rapidly involved. Compiler infrastructures like ARM can be a better alternative to GCC, and the source code to source code, bytecode to bytecode, and bytecode to native code compiler related technologies can ensure that Python-based domain-specific languages and their language side or their derivatives could be better suited for the application fields such like kernel scripting or kernel instrument. So in conclusion, Python is sure to play an important role in next generation software-defined systems. So it's time for Q&A. Oh, sorry.
Hello. I have two questions. So the first question is that how do you run the Python coding? I think I missed something in your talk. So is the Python code running directly on kernel space, or do you have some kind of callbacks from the kernel to instrument some functions?
Yes, actually we have demoed several samples about how Python, how to use Python script against some frameworks such like BCC or Kplex to running kernel instrument from user space. Yeah. So I think those projects those projects are all open sourced, and you may check their code on the GitHub. And we have illustrated some of their workflows and the architectures. And I think for a better understanding of this program, for the internal mechanism of how they work, you may just try the samples from according to what we mentioned today, or directly from their official website.
And the second question is that actually the source code size increase in Linux kernel mostly depend on the addition of network drivers. Actually, network drivers take many portion of the Linux code. So, do you think is there any possibility to use Python or splitting features for kernel to write network drivers?
Okay, thank you. It's a good question. I think this is what we really to represent how kernel scripting should be will be a great innovation in the future. Actually, developers from, as we have mentioned in this talk, developers from NetBSD has trying to use Lua for kernel development. As we can see that the kernel size, the code size of kernel has rapidly grown during the past 10 years. And as we know that half of the kernel code size against the Linux kernel is driver centered. Actually, in their implementation, NetBSD developers has implemented two drivers, as I remembered, include the driver for SQLite database. They have successfully implemented the two drivers in Lua, just in Lua. So I think using scripting languages such like Lua or Python to develop kernel drivers will greatly reduce the size of the kernel.
Thank you.
Thank you very much. Any more questions? Okay, thank you very much. That's all.
네, 회의를 마치도록 하겠습니다. 다시 한번 팽리님께 큰 박수 부탁드립니다.